Hey everyone! One of the first things when we talk about math and how we can use it for 3D and Houdini specifically is the sine wave. The sine wave is something that we've already seen in the expressions video. I think it was expressions 1 or 2. And there we used it to move things up and down. And we can actually do the same thing in Vex, of course, and a lot more, because now we cannot just, move a whole object, but we can move parts of it independently, like points, for example. So as usual, we start with something super exciting, a grid. So let's drop a point wrangle. And the simple stuff first, we can change the height of each point by the same sine wave. And as you probably know how a sine wave works, the input, controls the output, and the result is a curve between -1 and 1. And when we, for example, fill the input with the current frame, what we will get is that each point is moved up and down between the y element between -1 and 1 based on the current frame. Now let's slow this down a little bit, maybe by dividing this by 10. And then you can see, okay, great, you can move objects up and down. Now this might not seem like too much, but it's actually pretty cool when you do this with multiple objects. So if you have a case like this, and in this case, I made sure that the sphere is actually a primitive sphere, so that you could also just pack the whole thing. Oh, look, I did both. So I certainly have just points that represent one single sphere. And then, of course, what I can do is I write the same thing again, but this time I adjust this a little bit, and I'm not just using the current frame divided by 10, but I multiply this, or actually not multiply, we would add this, to add an offset, so to say, based on the current point number. So maybe just add PT_num or something like that. And then you can see that each point gets a different up and down movement. And this is already pretty cool if you ask me. We, can create complex movement that also feels good, because that's one of the nice things about sine waves. They slow down when they go closer to the extremes and speed up in the middle, so it tends to feel pretty organic and natural, and this is why it's a really cool technique, even if it's just as simple as that. And of course, and this is why I turned on pack and instance, if you don't have spheres but something more complex, of course you can still use the same technique by using, for example, the toy, by just packing it, and then it's also represented by a single point, and we have the same thing for more complex objects. And without showing this, but you will probably understand this at this point, you could also, instead of using PT_num here, use, for example, the class attribute, which you could create with a connectivity node, so you wouldn't even have to rely on packed geometry to make this work. Now this is pretty cool, but this again moves whole objects. What I want to do now is I want to change each point separately, and this I could do by, instead of using the frame, I could say, for example, move the points up and down based on their, let's say, position in the x-axis. So I just take the x element of the position, and this will create a sine number and set it to the height, and then we get this wave. And now the logic is, as you can see it, because it kind of does one whole loop, so to say, because it's between 0 and 1, we can actually increase that by just multiplying the input. And this is something we've already seen with noise. This would be the frequency. So this way we can increase the number of loops, so maybe 12. And then, of course, the overall height, which is the amplitude, we can just multiply at the end, something like that. And this is pretty much the same logic as we know from noise. And here, this quickly, you can create some, simple metal roof or something like that. I don't know. So deformation is possible as well. And of course, when you add an offset to this, just like with the noise, maybe a frame divided by 10 again, then the whole thing even moves. Well, actually, that's a bit slow, maybe something like this. So then the whole thing even moves. Of course, you can even combine those. So maybe you can take the y and add on top of this a second version of this. Currently, this is just two on top of each other. That's not what I wanted, but I could, for example, take the z position to kind of do the same. And then you can see I get this kind of shape, and it's even moving. And if I change the frequency and maybe the speed, then I can overlap those effects And I could even combine this by multiplying z and x to create some interesting variations, and I can create all kinds of interesting shapes. This is something that, you just have to play around with a little bit. I don't want to spend too much time on this idea. I just want you to understand that, combining multiple mathematical functions can create interesting combinations. That's all. What I do want to talk to you about is a very common use case of this, and that is we don't use just x or y, but we actually take from a certain point the distance. And the easiest distance calculation is actually to just say, let's say we create a distance variable, and then, for example, we just take the length of the current position vector, which would simply mean, of course, the distance from the current point to the center of the world. This is something we talked about before. And if you take this as an input to drive the height of a position, driven by a sine wave, it would look like this. And this is an important concept, that you can create kind of circular sine waves based on the distance to a certain point. Now, of course, the same rules apply as before. We can increase the frequency by multiplying the input. Doesn't matter which input it is, so maybe by 12, and you can see where this is going. And of course, we multiply the amplitude. There you go. And now we can create this kind of stuff. And of course, as before, we can add an offset. So maybe the current frame again divided by 5 maybe. And then the whole thing actually moves. Well, if we have to move it outwards, we invert it. So maybe minus in front, and then you can see it goes outwards. And let's make it a bit faster, maybe 3. And of course, what you could use this for is some kind of dripping effect or something yourself. Because what you could do as well is you multiply the whole amplitude, and let's actually do this in a new line because it gets a bit too long. You could multiply the whole amplitude by the distance. Now, just doing this like this will not help too much, but if you fit this distance, let's say we create a new fitted version of that distance, we could say, okay, we take the distance and say if it's between 0 and 1 meters long, then at its shortest, so distance from the center, it will be 1, and then it goes down to 0, and this will result in this. Maybe we can make the whole thing longer, maybe 3. And here you can see now you can limit the area that you want to use for this. So this is really powerful because it looks nice, and you could do all kinds of things with this. And of course, keep in mind, that's what I meant with you can combine mathematical functions. We can multiply the whole thing with a noise function. So based on the position in space, this looks then a little bit different. Let's increase the frequency. Maybe something like this. Oh yeah, maybe something like this. And overall by 3. And here you can see you can now even add a little bit of variation, so that to break it up a little bit, so that it doesn't look so perfectly mathematically even. And then if you do it right, it could even look quite natural. So this is the kind of stuff you can do with sine waves because, they create natural waves, natural up and down movement. Just overall, they feel very natural. And if you combine them with the techniques we've learned, you can create some interesting effects relatively easily. Now, what do I do if I want to do this not with the center of the world, which can be a bit boring, but maybe with a control node? Let's copy this. And the control node could either be literally a control node. I'm not sure if I showed this to you, but you can create control nodes, which are just made of a single point, which can be nice instead of a sphere. Let's do this instead of a sphere that we usually do. And of course, if you think about what we have to change here is, of course, the distance at the top, because currently the length of the current position is the distance to the center of the world. But we've learned before that we can just, for example, subtract a position from this. So let's call this P2. And what this position 2 could be is the point from the second input, or the position of the point, 0. And then what you get is that you can define a different reference point, so to say. And so now you can even move that thing while it's moving as well, by the way. And you can control this. If this is a bit too confusing to you, this length p minus pi p2, there is, in my opinion, an even easier way to understand, but it's basically the same thing. Again, we calculate the p2, and then instead of calculating the length of a vector, you can just say, okay, calculate the distance between my current position and the second position. Same thing, as you can see, I just calculated it and it's the same result. Maybe this is a bit easier for you to understand, but this concept here we actually explained in one of the last videos. So now we even have this drop water effect, or this puddle effect, I don't know how you want to call it, with a changeable reference point. And before we finish this, let's have a look at not only sine but cosine, just to make one thing clear, which people often don't understand, well, including me in the beginning, so let's be real here. When you have a sine wave, so let's do this again from scratch, maybe you can quickly try to do this yourself. What I want to have, I have a line here with 100 points, 300 points actually, and what I want to have is simply turn this into a wave. So of course what I do is I take a sine, control the y element of the position, and in this case the line goes into the x direction, so this should be driven by the x. This is the core idea, and now of course we can add the frequency, and this allows us to increase the frequency, and then we can also multiply the strength of the whole thing, so to say, which would be the amplitude. There you go. And what I wanted to show you here is what cosine actually is. So this thing is sine, and we just copy the whole thing over and replace the sine with cosine, which is just cos. And when we put them both on top of each other, you can see they're really just offsetted versions of the same thing. So if you would add an offset to this, maybe again our good old frame divided by 5, and we do this on both of them, then you will see they move in the exact same way. And this is just something to keep in mind, maybe, that the cosine is not, particularly complicated compared to a sine. It's really just an offsetted version. That's something I didn't know. Okay, so that much about sine and to an extent cosine. Play around with this and try to come up with some cool ideas what you can do with this, and then you will realize it's not actually that complicated if you just use it a couple of times. So I hope this is helpful. Thanks very much and see you later. Cheers.